All right, polynomial functions are what we're looking at. Polynomial functions. And I'm going to start abbreviating these as polyfuncs because it's quite long to write. So what I'm going to look at is just examples of polynomial functions and non-examples. There's a big long definition of what they are, and it's in the book, and I encourage you to look at it and read at it. All it's saying is there's coefficients times a variable raised to some power, and as long as they fall within certain guidelines. I'm just going to show you some examples that will help you, get through and understand what we're looking at. So first, let's say let's start with something that you're familiar with. You could have 3x plus 2. That's a straight line. So we've looked at those already. You could have a quadratic function. Let's say 4x squared minus 3x plus 2. That's a polynomial function. So we've already looked at these two things, and they are classified as a polynomial function. So just take what you see here with this g of x function, and now we can expand it even further. So instead of the highest exponent being squared, which is what a quadratic is called, now we can add a cubic function, which is 3, and a quartic function, and so on. So we can just keep making these exponents bigger and bigger and bigger, and adding more and more terms, and that's all a polynomial function is doing. It's just allowing us to take this quadratic and change it to give us higher exponents and even more terms. So it's just a bigger generalization of what we've already been doing. And there are certain rules that you can't have that will make something not a polynomial function. And I'll get to those here in a few minutes. So h of x, a cubic function falls under it. So if you have x cubed minus 6x minus 1, that's a polynomial function. There's infinitely many of these. I can write each one of these infinitely many times, different ways, and they'll still be a polynomial function. You could have a of x. We can go up to whatever exponent we want. We could say we have 37x raised to the, let's say, 389th power plus 17x to the 388th power minus 17. Something like that. So again, we can write these as long as we want, and it just keeps going and going. All these are polynomial functions. And this can be 100 million, it can be whatever number you want. It can be any number you want. It can be any integer that you want. Now we're going to get into the not polynomial functions, and this will show you some of the numbers that the exponents cannot be. So not polynomial, not polyfunc, not polyfunc. All right? So not polynomial functions would include if the exponents are negative, if the exponents have fractions in them, if we have any square roots, if we have any variables in a denominator. And all those are kind of the same. So what I mean is f of x, let's say capital F, we'll make this not. So if you have negative 3 times the square root of x plus the square root of 2 times x squared plus 5. So this is not a polynomial function, and it's because we have this square root here. You can't have your variable under square root and be a polynomial function. Let's see, capital G of x. I could have written this like this. So I'm going to write the same one, except I'm going to change this square root of x to the 1/2 power. And remember, if you have the square root of x, you can rewrite it as an exponent 1 over that fraction. So these are the same thing. This is also not a polynomial function for the same reason. Because of this guy. And because of this guy. Those mean the same thing. So you can't have square roots, cube roots, fourth roots, and similarly, equivalently, you can't have the fraction and the exponent. Then you can get into, let's call capital A, where you have a negative exponent or a variable in the denominator. So you can have 2 divided by x squared plus 7x minus 2. This is not a polynomial function because you have the variable down in the denominator. And then this means the exact same thing as that, as a 2 times x raised to the negative 2 power. If you have a variable on the bottom, you can bring it to the top, but you have to change the sign of the exponent. So in this case, it's positive. When I move it to the top, now it's negative. So you can't have negatives in the exponent. And for the most part, you're not going to be tricked on these types of questions when it comes down to the test. It's just getting a good idea of what's going on, what it looks like. And then graphically, let's say you have this graph. This is a polyfunc. This is an example of a polyfunc. All right, that's an example of a polynomial function. There's infinitely many of these. They can have however many terms in here that you want. The key here is to make sure that you have smooth edges like this. You flow real smooth, like there's no sharp corners and there's no gaps. You have continuity from beginning to the end. So smooth. We'll just say smooth. You just need to be able to identify. And then not a polyfunc. Let's say not polyfunc. We have another graph here. And let's see, you cannot have something like, let's see if I can draw it in. This is not a polynomial function because it's sharp, or it's a point. One more graph, and tell me if this is or isn't. So we have our x and y axis, and we have a graph that starts down here, and it comes up, gives us a solid dot, jumps down here to an open dot, and goes back up. This is not a polynomial function. Not a polyfunc. Because you have this gap in here, or a jump. Gap/jump.